Hi, welcome back to my Do It Yourself Python web series. If you are here for the first time, I suggest you to watch my previous short videos on this topic so that we can have a proper context of the content and as well as demos. And if you get a chance, please do subscribe to my YouTube channel and also download my Pizzapy database scripts mainly created for the SQL Server. Actually, I use the database in this Python series, so it will be useful and also you can follow along, right? So I'm also going to include all the links to any additional materials in the description, and I also write some articles and publish articles on my website called kishorsblog.com, and if you get a chance, please go ahead and visit. I'll include the link in the description also. So again, this topic is called Linear Regression Basics, and whenever we hear data science, we always hear creating models and also coming up with prediction equations. So in that context, I thought I'll put a small video for you to understand the basics and how this linear regression works and how we are going to use that in our data science experiments. But this video is exclusively for the linear regression, right? So let's get started. What exactly I'm going to do is that I have a Google sheet on my Google Drive. I'm going to open that to explain some basics. So what is exactly this linear regression is? If you look at the definition, it's actually a statistical method used to model a relationship between two sets of variables, and it's widely used. For starters, I would recommend that you use a simple linear regression and apply that on the data and learn some basics, right? So the main goal is we have some data and we're going to identify some variables in the data, and we're going to model a relationship between those variables. For this particular exercise, we're going to use two variables. There is also multivariable regression we can do, but that is again advanced topic at this point. So we'll focus on these two variables, right? So what is our main goal in this linear regression, and why do we use it actually? Again, our main goal is to apply this method, come up with an equation, and using that equation we can predict or maybe we can do some predictions on the data, right? So in order to do that, what we need is we need two variables, because that's the main purpose of this linear regression. So in this exercise, if you look at this Excel sheet, the Google sheet, you can see I actually mentioned it very clearly what exactly an independent variable here and a dependent variable, and I also put a comment saying that whatever value we are showing under that variable will be plotted in x-axis and the other one is in y-axis. So what we have here in the x-axis is a weekday number, something like Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. Instead of the name, we are representing the weekday in terms of number, and this number is constant, right? It will not change, and it is not dependent on anything else. So we're going to treat that as an independent variable here, and for each and every day we are also getting some orders, like again refer to this Pizzapy database. So let's say the day 1, which is Monday in this case, where we have orders like 2 orders, then Tuesday there are 5, right? Like that there are some number of orders. This is just only for 1 week, and if we have data for the past 2 years or 3 years or 4 years, and then we're going to use that data so that our prediction equation will be much efficient. So in this case, what we are trying to do here is that again, based on the actual linear regression definition, what we are going to find out here is that we have x, and here we just found the mean, in this case median x, and you can see that it's using this function called median, and the mean x in this case is 4, and mean y in this case is 4 again, like because we're going to change the values and see how it is going to impact these values. So what exactly this equation means is x minus mean x, and we're going to find those values here, and y minus mean y, and also x minus mean x and squared, what exactly is that value, and we also have a sum of those values, and here this is the product, like x minus mean x multiplied by y minus mean y, and we also have the product here. And now we have these values plotted here. In a sense, we have all these values showing here, and what we are trying to calculate is the slope. And if you look at the equation for the slope, it is nothing but f11 and e11. In this case, f11 is the product of this equation, and divided by e11, which is the product, sum of this equation. So we have a factor here called 0.107, and that is the slope. Basically, we are trying to draw a line. If you look at all these points here, we are trying to draw a line which is passing through all these variables so that it will be best fitted, and it will also the best represented on this graph, right? And we have another variable called intercept variable, where exactly it starts. So it has an equation as well. So if you look at that value, what we are looking at is the B14. B14 is mean y minus B16, which is slope in this case, multiplied by B13, which is mean x. So this is basically we are trying to figure out that what is B and what is A. This is just like a simple linear regression equation, right? Once we have all these values available, now we are trying to find out for every x value in this direction, what is the predicted value in the y direction. Again, it starts with the 1, 2, 3, 4, 5, 6, 7, because we have to calculate that y value for every x, and then plot those variables and draw a line touching those points. So here the equation is, it's very straightforward. B16, in this case, it is nothing but the slope multiplied by A4, which is x, and plus B17, which is intercept. So if you plot all those values, here it's like y is equal to b, and multiplied by x plus a. We have all those values here. So we are actually plotting a line on the graph, and these are the points, y points for every x you have here. So, but what is the equation? So Google, Sheets, if you go into this edit chart and customize, and if you go to series, you have this trend line. Like, let me change the color here, so you can see the trend line change color here. And if I remove that, the trend line is gone, and the data labels are gone, and the error bars are also removed. We just have only the data points here. But I'll start adding one by one. Again, trend line, and then we have data labels, and also we have error bars where you can see there are 2 points around this data point here. And there is also another option when you are there under the series section. You have use equation and also show R value. That is exactly the value here, which is nothing but, if you look at it, it is showing 0.107 multiplied by x plus 3r, and whereas R value which is showing here as 0.027, right? And we are actually interested in this equation. This is the equation we want for every x value. See that equation 0.107 multiplied by x plus 3 is the predicted y value. So for every x in future, if you have something, let's say with the data, if the data is changed here, and this prediction value will also change here, means prediction equation. And there's some interesting thing about this R value. The R value is actually called coefficient determination, which indicates that if I apply this equation, what I'm seeing right now here, 0.107 multiplied by x plus 3r, what is my efficiency? Right now the efficiency is 0.027. If I represent that in percentage, which is very less, right? What exactly that indicates? That means there are data points everywhere, like from 2, 5, 4, 2, 4, 2, 5, and it is basically very tough to predict. That's what exactly this percentage is showing here. Because these data points are very far from the line, and that indicates that anything you predict in future is not exactly going to be a foolproof prediction. So let me play with the values here. Let's say that we don't have any orders in the day 1, 2, 3, 4, 5, 6, 7, and this is also 0. See that right now the equation says 0 multiplied by x plus 0. It's basically you are not able to use the equation to predict anything. And at the same time, the efficiency of R, which is also known as R squared, which is right now showing no value at all. That means this model is not going to help us because our data is completely, in this case, is useless. So let me change these values to 2, and I'm going to increment by 2 just to see how this equation is going to change. 8, 10, 12, and 14. Now what exactly is happening here is there is a gradual increase in orders per day, right? 2, 4, 6, 8, 10, 12, and 14. And if you look at it, all the plotted values, the blue ones are the values which are actually coming from this the list. So 2, 4, 6, 8, 10, 12, 14. And then when I try to apply this linear regression, a simple method, and see that all the y values are also exactly the same. And if you look at the the equation, 2 multiplied by x plus 0. And the very interesting thing here is that R square value is actually showing 1. This is one of the important feature you need to always keep in mind, and you can get the equation by just applying the method. But what is the efficiency of that particular equation? Here R square has a range of 0 and 1. 1 indicates that it is 100% accurate, and 0 indicates that we cannot really predict anything. So because now everything is in a happy path, I can really predict what is the next value by applying this equation. Let's see that what exactly is that. If I have another x value called 8 and multiplied by 2, which is 16, and plus 0, which is nothing but the next value here. Anyway, we don't have more than 7 days in a week, But from the prediction point of view, if you just have 8 here somewhere, and if I apply this equation, I'll get a value of 16, which is basically the predicted value, right? But let's do something else. So now this is 2, 4, we'll keep it as it is, 8, 12, because orders can actually change by day, right? We can't really, we don't have a control on that. Let's say 3 and maybe some 6. So now what happened here? I have an equation now, 0.214 multiplied by x plus 4.71, and R value is 0.018. It shows that if I apply this particular equation for the value, imaginary value of 8 on the x, I may get some value, but by looking at the R value, I know that it is not really a good prediction, right? So this is how the linear regression works. So this is how you're going to implement it. And basically the idea behind the linear regression is you have an independent variable which is basically, you know, on its own, and you have a dependent variable. We are actually defining the dependent variable here as orders, right? So we are trying to establish a relationship between these two values and come up with an equation, and using the R square value we are also trying to see how efficient that equation is. That's what exactly the modeling you do in data science. This is very simple, but here right now I just have only 1 week worth of data, but in a real scenario you may be dealing with, you know, millions and billions of data, so that you have more data points here, and you have to run regression, and you have to come up with an equation that is called prediction equation, and then you need to keep a watch on this R squared value. Okay, so continuing from the previous example, let's go ahead and see what exactly we can do with the data what we have in our Pizzapy database. Okay, so here I'm actually going to use SQL Server Management Studio, and I'm using SQL Server 2019 with Python enabled. But anyway, I'm not going to execute any Python scripts from SQL Server in this video, and we'll do that in a later videos. So here, and I'm assuming that you have this database set up on your local machine, and you have all the scripts available in my GitHub project. You can download and you can execute them, and it's a very simple database, but to give you an idea, and that script actually creates all these tables, but initially order table will be empty, but if you run the second script, and you should be able to see some orders there. So I'm going to actually execute the statement count to see what we have in the table. We have around 70k records, and from a data profiling, quick data profiling perspective, you select top 10, and you can actually see the data in the table. We have order ID and the order date. Just pay some attention to that order date, which has a hour and also a minute component, right? And then we have all other variables like order source, store ID, topping ID, size ID, and extras, and everything. This is an indicator, but the most important thing is the quantity. So if I highlight all the records on that date, like 2014 January 1st, you can see that from 8 a.m. till 9 a.m. there were actually 4 orders, and each order has their own quantity. So from a data science experiment perspective, you can actually try to predict how your exactly day looks like every hour, but that will be very granular at this point. Also, you can predict in the number of orders or quantity you can expect for every day in a week, right? So here I'm using that order table, and I just transform that data into something which I can use quickly. I eliminated the hour component, the minutes component from this date, and I also introduced an hour here, so I am extracting the hour from the date and created a column there. And I also used a weekday number. This is the function, a date part and a date week, and I also created that as a numerical value instead of the name. And the quantity remains as it is because that's the record, right? That's the order. So I went ahead again, summarized the data, and this time if you notice that all the orders between 8 to 9 a.m. are now rolled up, and which is now the hour is showing as 8, weekday remain as it is, but now the quantity is summarized. And then again, I think this SQL, which is actually showing you at the every week day number level and what is the quantity. And now you can see the dates are actually in the individual records, means January 1, January 2nd, and then their respective numbers also, weekday numbers. I think this will actually show you the entire summary, because for all the 7 days, all the data starting from 2014 till 2019, and every day of the week, and if you roll up at that week day number level, these are the orders. Okay, so now you can pick any scenario, and if you remember from the previous discussion, what we are trying to do is that using this linear regression method, we are trying to establish a relationship between two variables by creating a model, right? So what are those two variables? So you can choose weekday number as your independent variable and the quantity as a dependent variable. So this way you can actually predict if your equation is good, and if your regression, the fitted line, if it is good, if it is close to all the data points, you can actually use that equation to predict the future demand, right? Like tomorrow, maybe next week, what exactly my week looks like based on every day. So anyway, use this database, go ahead and change all these queries. This will be posted on the GitHub as well. Once you have a good understanding about the data, because this is one of the important steps before we start going into this modeling exercise. So from here, what I'll do is that I'll switch back to the Google Sheet, and I have some tabs here. If you notice, the very first tab is that this example shows just only 1 week's of data, right? But here I added some more data. This is not from the SQL Server, because I just created this data in Excel, means Google Sheet, and I have around 50 records here, starting from 10/6/2019, and I use this weekday function to get the weekday number, and this is the name anyway, and the orders. So here I wanted to do something different. I think this is the same scenario we discussed in the linear regression example, but this time I'm using some data. So now again the same scenario, assuming that every day we have the same number of orders, which is very, very rare, but I'm just trying to show you the difference. But this time what I did, if you look at this edit chart, and it is actually taking a data range from C1 to D50, which is nothing but C1 to D50. But still our scatter chart is still showing only 7 entries here. That means it's basically summarizing all the data and applying all the regression formula, and then trying to figure out all that A, which is A and B, and then apply that equation here. So it's basically trying to figure out all the y points for every x based on the data what we have. And if you look at the equation here, it says that 0 multiplied by x plus 24, and then r squared value, which is right now not showing anything here. That means based on this data we can't really come up with any equation which we can use to predict anything. Okay, so because I just left all the values here as 24, and I actually copied everything into a next sheet, but this time what I did, I kept the data as it is, but in the order section what I did was that I'm just using a multiplication which is just like a 12 orders, and this is not exactly the real scenario, but what I'm using here is that if you look at the equation, C12, the day of the weekday number, multiplied by 12. Same thing here, so it increases double if you look at it, and 3 multiplied by 12, 36, and the same, exactly same here. And again I repeated the same here, so just to show you how it actually summarizes the entire data set into again 7 sections on the x-axis. The y-axis, again it is actually showing all the values. Now using this equation, right now if you notice that r squared value is 1, which indicates that our prediction equation is very efficient, 100% accurate. So again the same thing what I showed in the previous example, if I have an imaginary value here as 8, and if I use that 8 multiplied by 12 and that plus 0, and which is nothing but 96, right? So here I can see the value of 96, which I can predict very well. If it has an imaginary value of 9, which we don't have anyway, but we can actually predict that value precisely by applying this equation. In the other example, what I did was I used the same equation, C 2 multiplied by 12. I'm still using that 12 orders per day as a constant, but this time I'm just adding a random number adding to this orders. So again this random is applied, and as you can see all this data for the first 7 days are different, and again the next 7 days are also different, but I'm using this entire data set for this scatter plot, right? But this time still it kept on x-axis 7, because that's the group, that is the independent variable we are using, right? The dependent variable, it actually plotted all the values, but if you notice that the line, like in this case the fitted line, looks like it is passing through all the values, but you can still notice that there are some data points a little far from the line. Let's look at that. So immediately if you look at the r squared value, and the factor here it is showing as 0.98. So I always imagine this value in terms of 100%. So for me, when I see 0.98, it looks like it is 98% accurate. And then if you notice from the previous tab, this value was 12. Let's go back and check that. Yeah, it's 12. And even though I introduced the randomness, but because I still kept the constant of 12 orders per day, maybe we are still able to come up with an equation. This is basically a model. I would like to call it as a model, but the equation here is 11.9 multiplied by x plus 6.82. But in the previous case, it is just 0, right? But whatever is the equation here, I sometimes rely on this r squared factor to see how efficient it is. Now I can confidently predict the imaginary value here 8, because it is 98%. I'm at least confident that whatever value I'm predicting is actually close to reality. There's another tab I have introduced here called Outliers, and same sheet from the previous example, which is nothing but the random orders. Again, same values here, 12.1 and everything, but let's say that we have a day 10/18, we have around 300 orders on that day. Maybe there was some football game going on, or maybe there's a high school party or something like which is not expected, which is not in the normal pattern. Maybe sometimes it's a data issue which we don't know, but you can see that that particular value 300, I just added the value here. You can see that the data point is actually showing here 300. The line whatever we are drawing here based on our regression equation, this particular data point is very far from this line. And now what happened to this r squared value? If you look at it, it is now 0.46. That means it is 50% accurate just because of this particular one value. And so these value, this kind of values, the data points which are far from the line, fitted line, are actually called outliers. We don't know whether this is going to repeat in future. We don't know whether this is the data issue, or we don't know whether this is something like which we can really use in our prediction equation. Sometimes what we do is that we can get rid of that particular record because it's an outlier and it's one of a case in this scenario, and then we can automatically bring our r squared value close to 1. But again, you need to really pay attention to those outliers to make sure that those outliers are actually can be excluded, right? Otherwise your prediction will have again wrong outcomes. I hope this demo give you some basic idea on how to apply simple linear regression method on the data what we have, and also how to decide on independent and dependent variables. There is no thumb rule where we have to really identify these variables. It depends on your requirement, and it depends on what exactly you are predicting. And also I hope you have some idea on the impact of the outliers. Most of the time outliers will be eliminated because that's how you do as part of the modeling process. And the most important thing is that identifying the linear regression equation, what you see here, right? That is your equation. That is the equation you're going to use, apply on the x to find y. That is your prediction. And also the importance of this r squared factor. This will give you an indication. If it is 0, that means your prediction won't be really good, and if it is 1, your prediction is 100%. And it depends on the level of prediction and what kind of prediction you're planning to do. And some people they're happy with this 0.5 or 0.3 or 0.7. It depends on the data and it depends on your requirement. Okay, so what I'll do is that in my next video I'm going to show you how to actually write code in Python to implement this linear regression and come up with the model. And I'm going to use pandas, and I'm going to use NumPy and scikit to achieve that. Again, thanks for watching, and please do subscribe to my channel, and tuned for the next video. Thank you.